Okay, so I have started the recording as well. Okay, so I'll share my screen. I hope it's visible to all of you. I think this is lecture 16, I think. So first is we are going to discuss about normalization because we have already seen this part in our labs as well. Second is augmentation. And third is object finding, object localization in an image, object detection maybe. Detection in an image. So these three concepts we are going to study today. Okay, so first thing, we are going to discuss is normalization. So in normalization, there are two normalizing methods that are extremely important. First is min-max normalization that you have already done and implemented in your labs as well. Second is z-score normalization. So what is this normalization and why do we do this? So first idea behind normalization was so that my gradient descent would work faster. We have discussed this in initial lectures also. This works faster because feature range decreases. Feature range decreases. Decreases means suppose I have a feature range that is that varies from let's say from 0 to 1000, and if I am normalizing it, it will move from 0 to let's say 100. So this is normalized value. Okay, so this normalized value is basically, this means we are converting our range, we are reducing our range from this to this. Okay, so this is so overall when my range is decreases, this means I have to run much lesser steps in the gradient descent, much lesser step size is reduced basically. So that is why gradient descent would start working faster. That is why we do normalization. Now there are two popular methods for doing normalization. First is min-max normalization, and formula for this is, we have already you might already know this. X dash is equals to x minus min. This is for each and every attribute. Let's say a, for each and every attribute a, max a minus min a, and here it is, new max a minus new min a. Uh, this is underscore, this is also underscore, and then plus new min a. So what is min a and max a? I want to reduce, this is my I want to reduce my range from min to max, okay, and to new or n underscore whatever I have written. So this was n underscore min to n underscore max. So I'm reducing my range from 0 to 100 to 0 to 1. So my new min and new max is this. So if I put it in this formula, my range of x, any value x that is in the feature vector a, any value x, maybe it can be 100, 200, whatever it is. So this value would be reduced to x dash after my normalization. Okay, so this is how a normalization works. Now then similarly we have a z-score normalization. So in a z-score normalization, the formula is uh, x dash is equals to x minus mu by sigma, where mu is equals to mean and sigma is equals to standard deviation. Okay. So what is the difference in these two normalization methods? Over here also this value of x is reduced to x dash. Okay. And how it is reduced? Because suppose I have some example. Let's say I have 5 numbers 5 or 4 numbers, 10, 11, 9, then 9, let's say 8 and 12. So if I calculate the mean for this, mean is 10. Okay. So uh, basically what this is doing is, it's basically this is suppose 10. So 10 would be here, 11 would be here, 9 would be here, 8 would be somewhere here, 12 would be here. So what basically this normalization is doing, it is basically finding out the distance from the mean overall and subtracting it with the variance, dividing it with the variance. So that is what it is doing. So basically it is reducing my range. This is 10, 9 and 11, 9 and 11, sorry. So this is basically reducing this to values which is around 0, that is maybe 0.1, something like that. So basically this range is reduced, although but the idea is final range for this function, or if you find out normalization, x dash is equals to x minus 10 upon some standard deviation was, let's say some value 5, let's say. Okay, so x dash is for this 12th number or for this 8th number, it may not lie, normalized value, that is x dash will may not lie between 0 and 1. So this is the disadvantage of this z-score normalization, that the exact scale, it is not uh, converting my scale from initial range of x was 8 to 12, and it is not converting it into 0 and 1. So it is not scaling with respect to the scale that I want. Okay, so z-score normalization cannot do that, but in general scenarios we use z-score because z-score is z-score is suitable to outliers. It can handle outliers. Now what is an outlier and how does it handle? So this is advantage. So what is an outlier? Suppose in this set of points I do have one another point which is 20. So this is my outlier because it is not looking similar to rest of all the points. Now if I am using min max normalization, it will make all these values convert to okay, I will write it. Suppose I have values, example, suppose I have values 20, 8, 9, 10, 11, 12. Okay, so this is my outlier. Now if I apply min max, so it will give me some value. It will change the range to 1, and this would be changed to 0. This would be changed to 0. ठीक है, and 0.1, 0.2, 0.3 and 0.4. Rather than it should be, this should be between 0 to 1, it is considering this as 1. Why? Because this 20 is extremely larger. So this is outlier. So min max does not perform well for outliers. ठीक है. While in z-score normalization, if you apply z-score, it will give you values such as 0 or maybe this should be 0.5, this should be 0.9 and 0.8, maybe 0 point something like that. I'm not sure. Please calculate. So, and this it would give you 1 point something, 1.2. So it's showing that okay, this it's doing it is perfectly handling the outliers. Okay, so that is why we are more inclined towards a z-score than min max. So when we want to change the range to perfect 0 to 1, then we do min max. For example, in images you can see the range is always 0 to 255, so there is no chance of outlier. It cannot be 400 or something like that. So that is why we do min max normalization over there. Okay, it can happen, but that is the error. Okay, so this was the normalization. Now next method is augmentation. Uh, so in augmentation, in data augmentation is another way of reducing the overfitting. Augmentation. artificial. Okay, it's a way to reduce the overfitting in the data. Now in the image data, it's for, let's say, I'm doing for image. So suppose I have image of let's say cat. Okay, so assume this is a cat. So I have image of a cat. So what data augmentation does, I have let's say I can only click 1,000 pictures of cat. ठीक है. So if I want to train a CNN model, this 1,000 pictures is very less. So that is why we apply augmentation. So augmentation, what this does is, we are basically, there are many methods to do that. Let's say it will do mirroring, it will do cropping, it will do so many methods are there. Rotation, ठीक है, rotation, shearing, ठीक है. So all these operations, so what it does is, it takes only one picture, and it suppose if it's applying cropping, so in cropping what it does is, it takes it randomly crops the whole picture. And basically random cropping is, suppose it has clicked the face, then again it has clicked the uh, other part, eye, maybe eye of the cat. ठीक है, so like this. ठीक है, front face. Or so from one image it is generating multiple images. In another part it has cropped something else. ठीक है, so like this. So from one image it is generating 4 images. So this is called augmentation. Similarly, if you mirror this image, you will suppose this is the image. So if you mirror this image, you will get something like this. Okay, okay. So this is the mirror of this original image A, and this is mirror of A, है ना? So this one image is converted into this one and plus one. So I have two images. So now all these images I would give as input to my model, and to train my model. So what is the idea behind this is, for one image I can do rotation as well, I can do shearing, I can do mirroring, I can do randomly cropping. So I have multiple images now. Now I can give all these images. So my 1,000 image data is converted and increased to some 4,000 or some 5,000, maybe some images. Okay, so idea behind is to increase the data set. Now if I have increased the data set, so I can so increased data set means, increased data sample means I have reduced the overfitting. Okay, so this is the idea behind data augmentation. Okay, so I hope up till now everything is clear, because this was, if you have any doubts, you can ask. Okay, so let's discuss the next concept, object localization and object detection in an image. So up till now, what do? Is we have an image and we classify, we tell whether it's a cat or whether it's a dog. Now, what if I have image and there is some object one, and there is some object two. Is somebody wants to say something? Okay, so I have suppose object one and object two. ठीक है, I want to, this is let's say flower. ठीक है, one flower I have. Flower is a little bit small object, maybe something big object, maybe a car. ठीक है, so this is a, let's say, car one. This is, let's say, car two. Make it look like some car. I don't know how to draw this. ठीक है, so imagine this is a car. Now what I want to do is, I want to basically draw a bounding box uh, around this car. I want to identify whether there is a car in my object or in my image or not. So what I want to do is I want to draw a bounding box about around this, and I want to do like this. So this is called object localization. Localization means I'm basically identifying that where the object is present or it's present or not. Okay, so this is the idea. Now how to do that? So for doing that, what do I need specifically? So for doing that, for identifying the position of the car, I would need the position of the center, right? I'll use another pen, let's say green. So I would need a position of this center of this car, okay, and I would need the height and the width, right? These four things I would require, and I would like to know whether it's a car or not. Okay. So what are the outputs? Right now, I will classify it as Y, that is a car or not. So yes or no. Okay. So I have output. So first output right now in classification, car or not. Okay. Second thing I can give is a localization X and localization Y. This is the center point of the object. Center of the object. If my car says yes, if the object, if my output Y says yes, this is a car, then it should give the center of the object, that is a center position. So this is my Lx comma Ly. Also what it should give, it should give the height and width. So I will say, let's say bx, and it should also give the by. So this is so bh, sorry, bh, bh, and this is bw. So this is width and this is height of the object. So now my output y is changed from this one to this whole y. Okay. So for one object, how do I what are the parameters that would be there in the output? It should be car, whether it's present or not, yes or no, one. Two, second is x, third is y, fourth and fifth. So five parameters. So basically five output labels. So one output label is converted to five output labels to identify whether that car is present or not, and what is the position and what is the size of that car, right? So this is called object localization. Okay. Now there is how do my loss function in this case would behave? So my loss function in this case would look something like loss function, that is my output predicted and actual output, difference of actual and predicted output. It will look something like this: y1 minus uh, y1 square plus y2 minus y2 cap square plus up till y5 minus y5 square. Okay. So this is in case if my y1 was 1, that is if car was present. If car was present, it should output the x, localization x, point ly, width, width and height. Okay. So if car was present. Now if car was not present, y1 equals to 0. In that case, my only error is y1 minus y1, y1 cap minus y1. Why? Because we don't need lx, ly, width and height in that case. So if my car was not present, in that case, what would be the output? y1 minus y1 square. That is whatever. This is the output of the softmax function. Okay. So how many neurons in the softmax function? 1, 2, 3, 4, 5. So this is car present, yes or no. If yes, what is the lx, what is the ly, and what is the height, and what is the width? So this is, and rest all the neural network would be same. Okay, so this is my softmax output would look like. Now what if I had multi-class classification? um, Suppose what if I had for multi-class, I have three classes: car, bus, and bike, and let's say, okay, it was not a car, it was not a bus, not a bike, and something else, maybe background. So in that case, there is no yes or no, there is addition, that is background. Okay. So in case of no, we can call it background. That is background of the image. That there is no object was present. It was just the background of the image. Okay. So now my output label would look something like number of classes. That is C1, C2, C3, and C4 for each of these, because classes were only three. C1, C2, C3. This is background, means no, none of the class was present. Okay, so none of the class represents C4. And then how many parameters would be here? Um, for first object, its position. So second object, its position. Third object, its position. Okay, three objects and their positions, three objects and their heights, and three objects their widths. So for first position, it was x1, x2, x3, then again x11, x21, x2, x31. Then again for second, it should be y11, y21, y31. Then it should be height and width. So height h1, h2, h3, and width w1, w2, w3. So this is overall uh, my cost output softmax layer would look like. I hope this is clear to you, or is it a little bit confusing? So tell me if it's confusing.
Please explain multi-class once again. Like this
Uh,
softmax, how you use.
sure, sure. Okay. ठीक है, तो I will delete this part and I will explain multi-class in a new page. ठीक है, चलो let's see multi-class again. Multi-class में, let's say I was having class 1, class 2, class 3. This was car, this was, let's say, bus, and this was, let's say, bike. ठीक है, I had three classes. So this I will uh, add add one more class, that is C4, which is none of these is present. None of these is present. Or we can say that background is present. Background of the image is present. Okay. Now for C1, what do I require? If it output if C1 is equals to 1, it should output what? It should output the position of C1. Okay, C1 position, that is center position. It should also output the height of C1 edge. It should also output the width of first object, right? Up till now, no confusion. Again, if C2 is 1, in that case, it should also output C2x, C2y. Xy is the position of that object. Then it should also give height, and it should also give width, right? Then similarly for C3, if C3 is present, in that case it should give C3x or C3y, and C3 height and C3 width. So how many total number of outputs do I have? Also for C4, if C4 was present, if C4 is 1, in that case, nothing is required to give as output. Okay. So how many total number of parameters in this case? Sorry, output in this case. So this is 4 plus 4 plus 4 plus 1, right? So total number of outputs would be 17. Sorry, 13. Right? So this is what my softmax layer would look like simply. So it will look like, I will draw it. So I had just drawn this uh, I have drawn just these in a layer format. So this is my first neuron. It is for, let's say, C4. Then for C3, it is C3X, C3Y, C3H, C3W, and then up to all the 13 parameters. So so how many neurons in the softmax layer? It would be 13. ठीक है? So this is the idea. अब it's still not clear.
It's clear. Thank you, ma'am.
Okay. ठीक है. So this is also called the landmark. इसको generally हम landmark भी बोल देते हैं. The C1, this position of the object, and if I'm asking for the center position, so this LX or LY, so इसको we also call this as landmark. Landmark, or the middle position of the object, center position of the object that we want to find. ठीक है. So this was the landmark detection. Similar is the now for object detection, for detecting the object detection, what do we actually do? Suppose uh, I have this image. This is a big image. Now, what I want to do is I want to find out whether the object is present in this whole image or not. Okay. So I will put a filter over here. So this is a very big image. Imagine it something like. Okay. So I will put my filter over here at this position, and I will apply the convolution layer. So position 1. So for position 1, I will give as input, and I will apply convolution network. Pura whole CNN I will apply, and I will take as output. If it says yes, okay, so it will output me the position of that object if object is present in this particular location. Okay, so if object was present over here, so it will give me output yes. If object was not present, it will give me 0. Okay. Next position for the filter, I would slide it to a slightly different position, and I will keep filter over here, and I will repeat the process. So for position 2, I will apply CNN, and I will again I will check whether the